Have you ever been in that situation, maybe looking at some wiring thinking, I need to know how much current is flowing here, but the idea of messing with live circuits or cutting wires just feels, well, way too risky.
Absolutely. It's a really common hurdle, especially if you're just starting to get comfortable with electrical concepts. It seems like you should be able to measure it, but how do you do it safely?
Exactly. So today we're doing a deep dive into a device that's honestly quite brilliant in how it solves this exact problem, the clamp meter.
Ah, the clamp meter. A fantastic tool.
It really is. It basically revolutionized how we measure current, didn't it? Made things so much safer, so much more convenient for, well, pretty much everyone.
Definitely. It moved current measurement from something potentially hazardous and disruptive to something quick and non-invasive.
And our mission for this deep dive is to really unpack the how behind it. How does this thing actually work? We want to break it down so it makes sense, even if electricity isn't your strong suit yet.
Making it clear for beginners, right?
Precisely. We're drawing inspiration from a great source for this controlling, essentially, real beginners, step-by-step electricity. The whole point is that beginner-friendly explanation.
And it's fascinating, isn't it? How a core physics principle, something you might see in a textbook, is applied so cleverly in a practical tool like this.
It really is. We're not just looking at what it does, but exploring the why. Why is it such an elegant solution?
Let's get into it.
Okay, so maybe let's start with the problem it solves. Before the clamp meter, if you needed to measure current, you used a standard ammeter, right?
Correct. A traditional multimeter set to measure amps or a dedicated ammeter.
And how did you have to connect that? Because that's the key issue, isn't it?
That is the absolute crux of the problem. You had to connect it in series with the load.
In series. Okay, can you maybe unpack that a bit? What does that actually mean in practice?
Yeah, think of your circuit like a closed loop, maybe like water flowing through a pipe. To measure the flow in the pipe with an old-style meter, you'd literally have to cut the pipe open.
Cut the pipe, okay.
And then insert your meter into that break so the water flows through the meter itself. Electrically, it's the same idea. You have to physically break the circuit, cut a wire, or disconnect something.
Right.
And then insert the ammeter probes into that gap to complete the circuit through the meter.
Wow. Okay, that sounds inconvenient at best.
Inconvenient is putting it mildly.
Hmm.
First, it almost always means shutting off the power. You can't usually cut into live wires safely.
Definitely not something you want to do casually.
And no. And shutting down power can mean costly downtime in factories or just a major hassle at home. Plus, there's always the risk involved in modifying wiring, even with the power off.
So the need for something better was pretty huge.
Immense, especially for troubleshooting and maintenance where you need quick, safe readings without disrupting everything.
And this is where the clamp meter becomes the hero of the story.
Exactly.
Because it completely sidesteps that whole issue. No cutting, no disconnecting.
None at all. You can clamp it around an insulated wire while the circuit is live and running.
You just put the wire inside that loop part.
That's right. That distinctive jaw, or clamp, often a sort of reddish color on many meters, is the key. You open the jaw, place it around the single wire you want to measure, and close it.
So how does it do that? If it's not touching the copper, how does it know the current? Is it magic?
Huh. Not quite magic, but it relies on a really fundamental link between electricity and magnetism. It's a core principle. Whenever electrical current flows through a conductor, like a wire,
Okay.
it automatically generates a magnetic field around that wire. It's invisible, but it's there.
Like an invisible force field.
Sort of, yeah. Think of it like invisible circles spreading out from the wire. And here's the crucial part. The stronger the current, the stronger that magnetic field becomes.
Ah, okay. So more electricity flowing means a bigger magnetic field around it.
Precisely. And the clamp meter is designed to detect and measure that magnetic field.
So the clamp itself, the jaws, they're interacting with that field.
Exactly. Those jaws aren't just plastic. They're typically made of ferrite, a special magnetic material. They act like guides, concentrating that magnetic field produced by the wire's current.
So they grab the magnetic field, in a way?
They capture and channel it, directing it through a part of the meter hidden within the clamp mechanism itself.
Okay, so the clamp collects the field. But then what happens? How does a magnetic field turn into a number, an amp reading, on the screen?
This is where another law of physics comes in. Electromagnetic induction. You might have heard of Faraday's law.
Vaguely, yeah. Like with generators.
Exactly that principle. It states that if you have a changing magnetic field passing through a coil of wire, it induces a voltage, an electrical signal in that coil.
Okay.
Inside the clamp meter's jaws, there's a small sensing coil. When the magnetic field from the wire you're measuring is channeled through those Faraday jaws, it passes through this internal coil.
And because the current in the wire creates the field, that field causes a signal in the meter's coil.
Precisely. The magnetic field, created by the current in the wire, induces a very small voltage or current in the sensing coil inside the meter. It's like the wire's magnetic field is talking to the meter's coil.
A kind of magnetic whisper, maybe?
That's a great way to put it, a magnetic whisper. And the loudness of that whisper, the strength of the induced signal, is directly proportional to the strength of the original magnetic field.
Which is proportional to the current in the wire.
You got it. So
Yeah.
bigger current, stronger field, stronger induced signal in the meter's coil.
And then the meter just measures that tiny induced signal.
Yes, that small signal is then amplified and processed by the meter's internal electronics. It's carefully calibrated so that the meter can display an accurate reading of the actual current flowing in the wire you clamped around.
All without ever making electrical contact. That's genuinely clever.
It really is. It allows for safe, non-contact measurement. Think about checking a high-current motor or troubleshooting equipment without any risk of shock or needing to shut things down.
It makes perfect sense why it's become such a standard tool. But you mentioned clamping around a single wire earlier. That sounds important.
Oh, it's absolutely critical. This is probably the most common mistake beginners make. You must clamp around only one conductor at a time.
Not the whole cable with multiple wires inside.
Definitely not. If you clamp around, say, the entire power cord going to an appliance, you'll likely read 0 amps or something very close to it.
0. Why would it read 0 if there's current flowing?
This goes back to how AC circuits typically work. In a simple circuit, you have current flowing to the device in one wire, the hot or live wire, and returning from the device in another wire, the neutral wire.
Right, going out and coming back.
And crucially, those currents are flowing in opposite directions at any given moment.
Okay, opposite directions. So what does that do to the magnetic fields?
Well, if the currents are equal and opposite, the magnetic fields they create are also equal and opposite.
Ah, so they cancel each other out.
Exactly. Like adding +5 and making it 5, you get 0. If the clamp is around both wires, the meter sees the combined magnetic field, which is essentially 0. No net magnetic field means no induced signal in the meter's coil.
So the meter just thinks there's no current flowing, even though there is.
Correct. That's why you have to isolate just one wire, the hot or the neutral, to measure the magnetic field from that single current flow. Then the meter can hear that magnetic whisper clearly.
That makes complete sense. It's not just about physically fitting the wire in the clamp. It's about isolating the magnetic field you want to measure.
Precisely. Understanding the cancellation effect is key to using the clamp meter correctly.
So let's sort of wrap this up. What's the big picture here? We've seen the clamp meter cleverly uses that fundamental link between electricity and magnetism.
Right. Current creates a magnetic field.
And by sensing that field non-invasively, using electromagnetic induction, it gives us a safe, convenient way to measure current without breaking the circuit.
It's a fantastic example of applied physics solving a real-world safety and convenience problem. It makes electrical measurements so much more accessible.
Especially for beginners, going back to our sources theme, it lowers that barrier to understanding and working with electricity safely.
Definitely. It removes a major point of intimidation.
So maybe a final thought for our listeners to chew on. As you look around, at the technology we use every day,
Yeah.
how many other tools or devices might be using invisible forces like magnetism or maybe light or sound in these clever, indirect ways to measure something or make something work?
That's a great question. The clamp meter is such a clear example, but the principle of sensing things indirectly, reading those whispers, is everywhere once you start looking.
What other sort of aha moments are hiding just beneath the surface of the tech we take for granted?
Makes you think, doesn't it? About the hidden ingenuity all around us.
Keep those curious minds buzzing, everyone. Thanks for joining us on this deep dive.